Day 3 notes. This is unit 6, day 3. This is side 2 of the notes. Now we're still going to be building component vectors, finding velocity, but now we're going to have to consider gravity, and we're going to have to consider time. So it's a little bit of a difference, a little bit of an addition, but hopefully nothing that's going to be too complicated. So here, a ball is tossed up in the air at an angle of 70 degrees with the horizontal and with an initial velocity of 36 feet per second. Neglect air resistance and gravity. Give the velocity vector, and what does this mean? Now, I'm going to change this up a little bit. I'm going to go ahead and give you the equations that we're going to need to use to solve this type of problem. It's going to be a little bit different than what we've been accustomed to. So we're going to start with our magnitude, which is 36. That's our initial velocity. But now we're going to write t for time, then cosine, and our angle is 70 degrees. Then we're going to do 36 again, which is our velocity, t for time, and now sine of 70 degrees. Now this equation is going to help us answer these problems here. Specify the position of the ball as a vector at 1, 2.5, and 4 seconds after the ball is released. And here's what that means. For each one of these examples, you're simply going to substitute the number for t here and there. So let's start with at 1 second. We're going to find our cosine value first. So 36 times 1 cosine 70 degrees. That would be 12.313. And now we have to do the exact same thing, but this time with sine. 36 parentheses 1 sine of 70. 33.829. That is the component vector after 1 second. Now do what I just did, but do it for 2.5 and 4. And let's see if we get the same thing. Continuing on, 1c, express the position of the ball at time t, where t is the number of seconds after the ball is released. That's what we did here. For some reason, they wanted you to do this after the fact, but I thought that didn't make a lot of sense. So I went ahead and took care of that step. And then if you just would like to copy this portion down write the general vector that can be used to model motion with parametric equations. Here it is, magnitude times time times cosine of theta, magnitude times time times sine of theta. And how does this differ from what we've learned in our vector problems? Well, we now have time to contend with. Side 3 of the notes. Does the description of this problem, all that stuff that we just solved for, does it provide a realistic model of a thrown ball? Why or why not? Why, no, it doesn't. Because we live on Earth. And on Earth, we have gravity to consider. Let's try to model the ball a little more realistically. It is a fact from elementary, my dear Watson, physics, that on Earth, the effect of gravity vector is that add the gravity vector to the position vector we determined previously. Now your x, which is here, your horizontal, this is the horizontal effect. It's going to be the same. 36t cosine 70. It's the y value. Y is vertical. Gravity has an effect on the vertical. So our formula here is going to change just slightly. So 36t sine 70. Now we have to contend with gravity here, minus 16t squared. So how far does the ball travel horizontally after 2 seconds? Now remember, this is the horizontal. And this is the vertical. You know what? Let me write that differently because we're not using that formula anymore, are we? Horizontal here. Vertical. So, part B, how far has the ball traveled horizontally after 2 seconds? And how high is the ball at that time? So we're going to need to first use this formula here, and wherever we see a t, we're going to substitute a 2. Let's plug that into our calculator. .625. What are we dealing with here? Feet? Let's just say feet. It has traveled 24.625 feet horizontally after 2 seconds. And now, how high is the ball at that time? So now we're going to take this formula here, and everywhere you see a t, you're going to plug in a 2. Now be careful whenever you plug 2 in for t squared, you gotta do it like that. Let's plug that into our calculators. So at 2 seconds, it is 3.658 feet above the ground. How long does it take for the ball to hit the ground? We're going to want to use the vertical equation here, but here's what you would need to do if we were solving this on paper. You would need to set your equation equal to 0 and solve, because 0 represents the ground. But what we're going to do is we're going to use our graphing calculator, and we're going to plug this into a graph. It's going to make it a lot easier. So we'll go to y equals, clear out any previous data, and then let's input the vertical formula here. 36 They say t, but you can use x, same thing. Sine 70, close parentheses, minus 16x or t squared. Let's graph it. All right, now our x-axis here, that is a representation of the ground. The ball starts here, travels upwards, and then hits the ground, boop, right there. Now, this is pretty easy if you remember these steps. Now, if you'll see right where my pen is pointed, that is where x is 1 on the x-axis. That's where x is 2. That's where x is 3. That's what all those little hashes represent. So it looks like the ball falls somewhere in between 2 and 3 on the x-axis. So here's what we can do. Second, trace. We want to go and highlight 0 and then push enter. And then remember, we've already identified, it looks like the ball is falling somewhere in between 2 and 3 on the x-axis. So we're going to do 2, enter, 3, enter, and then hit enter one more time. When y is 0, that tells you where the ball has landed according to the x-axis. So our answer would be 2.114 seconds. That's how long it's going to take for it to hit the ground. Now, find the maximum height of the ball, and how long does it take the ball to reach that height? We have already put in the formula that we need to solve this, so we don't need to input that data again. So let's go to second, trace. If we're trying to find the maximum, now let's highlight maximum in our calculator, hit enter. Now your maximum, even though it doesn't quite fit on my calculator here, the ball is doing something like this. This would be the maximum point right there. It's going to go no higher than that. So our maximum, yes, it's off doesn't quite fit in the plane here, but it's somewhere here. So that looks to be, according to our x-axis, in between 0 and 2. 0 and 2. Somewhere in between 0 and 2, we're going to find our maximum. So let's do 0, enter, 2, enter, enter one more time. And we have an x value and we have a y value. This is our vertex. We want to write down both bits of those information, starting with the x value of 1.057. And then we have a y value of 17.881. Now we have our vertex here. Your x value, that's time. I was about to put seconds, but I'm just going to put time. And your y value represents elevation. So how long does it take the ball to reach that height? Right there, 1.05 seconds. What is the maximum height of the ball? Right there, 17.881 feet. Part E, how long does it take the ball to travel 18 feet? Now that's horizontal. So we want to use that horizontal equation that we wrote up just a little bit above my paper, which currently isn't fitting on the screen here. That horizontal equation is 36t cosine 70. We want to know how long is it going to take it to travel 18 feet. So we need to set this equation equal to 18 feet. So here's what the goal is. We want to isolate t. We want to get t all by itself. This equation reads as follows: 36 times t times cosine of 70. The opposite of multiplication is division. So in order to get t all by itself, we're just going to divide both sides by 36 cosine 70. So this right here, that's what you're going to want to plug into your calculators. Alpha y equals enter. I would use the fraction symbol here. 18 over 36 cosine 70. 1.462 seconds. Now, how high is the ball at this time? You ready for your minds to be blown? Here's what we're going to do. Remember, we have already put in the equation to solve for elevation, to solve for height above the ground. So here's what we can do. We can hit second window, and we can tell our calculator exactly what we want our table to read. Well, for solving for how high is the ball at 1.462 seconds, on the screen, you're going to want to hit 1.462, enter. And now hit second graph. And it tells you exactly how high the ball is at 1.462 seconds. That is 15.259 feet high.